I would like to talk about some reinforcement learning methods applicable in traffic control. And just briefly about me, so I am working at the Budapest University of Technology and Economics in Hungary, and I'm working at the Faculty of Transportation Engineering, and more specifically, I am leading the so-called BME, which is the abbreviation, Hungarian abbreviation of the university, so the BME Traffic Lab. This is a small research group about traffic-related research, and these are our main activities, competencies. So we are specifically focused on traffic issues, not the vehicle parts. Of course, we are also looking for the vehicle problems, but we are interested in traffic modeling, simulation, traffic estimation, prediction, and traffic control problems. We are a small group with a few researchers who are also university professors and the 5 PhD students, and we are doing scientific projects, Horizon European Union projects, and other kind of bilateral projects. Also, we are working with the industrial projects. We have now running projects with networks, Google Research, and also national companies and authorities in the road traffic. And which is very important in our days is the collaboration work with the newly built automotive test track facility in Hungary, which is called Zala Zone. This is a very new automotive proving ground, which was specifically built for CCAM, so the new era of transportation and mobility testing. Today's topic is coming from the laboratory research, of course. And now I would like to talk about two topics, which is coming from one of my last year PhD student, Shuan Feng, and the second one is from a last year master student and hopefully next year a PhD student at me, Pengyu Zhang. The first topic is about the network, the intersection level control, and the second one is the network level possibilities for traffic management, which is common in both research, that is the applied methodology, which is based on the reinforcement learning, and secondly, we love using traffic simulation, so we always make experiments and validation using microscopic traffic simulations, usually SUMO or other software tools. So let's go ahead with the first topic, which is the multi-agent reinforcement learning based traffic control for urban intersections. But very important that we are not seeking now yet another traffic light control algorithm, but we focus on a novel approach, which is well known on the freeways, but not yet used in urban context. This is the variable speed limit policy. So the background is that the known issue is obvious for everybody of the urban intersection, which are big bottleneck point and also high probability spot for accident day by day. And there are solutions for intelligent or traffic responsive or adaptive, or there are a plethora of expressions for smart intersection solution with traffic lights. But the real world, I don't know what, of course, it might be different perhaps in other part of the world, but in Europe and also in the United States, most of the intersections are fixed time still now, or partly traffic responsive systems, so with some adaptivity, but in a very limited way. And changing this situation is not easy and obvious due to very simple operational and policy reasons, very struggling to apply new methodologies if the road authority is the owner and the operator of a given intersection and so on. So it's not too easy to make smart and high-tech an intersection. And that's why our motivation is to provide a solution which is very practical. So we just consider the traffic lights in terms of control theory as disturbances in the system. So we accept how it works, and we try to emulate the system without the traffic light control, which is hard to get accessed. So that's why we are focusing rather on the car capabilities. And in this slide you can see the VSL, so very speed limit control on freeway, which is quite a well-known process and works very powerful and very efficient to prohibit big jams or smooth the traffic based on the classical fundamental diagram of traffic. And our approach is very similar, and in an analogous way, we are looking for application in urban context based on the new perspective of automotive vehicles, because everybody knows that automotive companies and industries in advance compared to the road authorities and infrastructure operators. So we think that year by year we are close to the situation that the car will be V2X capable, and they will be able to accept easily data from the infrastructure or from each other, even without the fully autonomous capability. Okay, so let's go fastly through the classical solution for VSL control, like rule-based solution, or the model-based methods, which can be open loop optimization or classical feedback control. But all these classical variable speed limit solutions has some limitations in terms of flexibility and the model, the needs of model. And that's why our approach is to substitute this approach with reinforcement learning. And the main advantage is the model-free concept, and of course, the online learning capability of the reinforcement learning. So that's the main point. For example, a traffic light operation in a general intersection in a city is usually based on fixed time or with some flexibility, but the traffic signal programs are switching using a clock. So the same traffic light happens in the morning and another traffic light in the afternoon and so on. But this is, as I mentioned, this is assumed to consider as a disturbance, and this is a changing environment. So that's why online learning capability of reinforcement learning is very advantageous. So that is our concept, and we apply the multi-agent proximal policy optimization, the so-called MAPPO method, in our research. So the control framework you can see here briefly, and we tested this framework with an intersection, not so simple intersection, but an intersection with 4 legs, and the multi-agent are the 4 junction legs in our case. The states are the Q lengths of each road sections or legs, and the action variables are the different discrete speed limit and the reward. That is the negative value of the standard deviation of the vehicle occupancy on the different road sections. So briefly, via the reward function, we try to smooth the traffic by minimizing the variance. So that is the point, the variance minimization of the traffic density. Okay. We did the simulation tests on a real-world intersection. So we chose a Budapest intersection. Here you can see the location. this is a quite big intersection with several lanes, with several turning options, and we programmed it with the real-world signalization. And here you can see some results with the current, fixed speed, limits control, what happens normally in this intersection in the morning. And on the right side, you can see the reinforcement learning based speed limit control. And what is important here to see, this is like a heat map. So the occupancy level is shown by colors, and the colder are the legs, the smoother are the occupancy. So probably you can observe that the right side is more cold in terms of heat map. But you can see also a leg on the south, which is quite similar on both sides. And this is due to the limitation of the current fixed time traffic signalization. So of course we cannot do a miracle, but still we can ameliorate the whole system efficiency. But here on the south leg, the left turn green light is so small time that we cannot really ameliorate this part. But in all, the whole system provided better results. Here you can see also other results in terms of spatial temporal distribution of road section occupancy. You can see the left side the fixed speed limit control, and on the right side the reinforcement learning based speed limit control approach. And you can see the four legs of the intersection, so the north, south, west, and east legs. And again, here you can see the heat map that a bit much colder are the legs on the right side, except the south, which is per se very limited in terms of traffic green light. Okay, and another performance measure we investigated in this research is the so-called surrogate safety assessment model, the SSAM, which is also not only a model, but also software, an open source software grade tool to analyze accident hazard probabilities, specifically based on trajectory files, which are coming from microscopic traffic simulators. And please note that in SUMO or VSIM or other microscopic traffic simulators, we cannot model accidents because they are not accident simulators, of course, but we can analyze different thresholds and different parameters of each cars based on the trajectories, and that can be very useful to analyze in terms of safety the traffic system. And a few results you can see here. For example, our approach with the RL-based VSR control reduced the total traffic conflict almost by 10% in general, and also the rear-end conflicts was reduced, the lane change conflict as well, and the average maximum deceleration value was also lowered significantly. So in all, we can say that the main goal to smooth the traffic, so to avoid as much as possible the stop and go and the backward speed propagation was achieved. So that was the intersection level method. And now I would like to skip to the network level solution with, again, using reinforcement learning. And this is about routing, individual and socially optimal routing questions we investigated for autonomous vehicles. So the background is, again, well known, that we know that routing is crucial, or will be much more crucial in the world of future cars, And we also know that knowing and collecting real-time and historical traffic data very well pattern can be revealed to understand the dynamics of the traffic in a given network. So the traffic demand can be distributed or assigned in an optimal way if we want. But the eternal question is here again, that there is a so-called user or individual optima and social optima, and they are not in aligned always. So of course, if you are a user, or I am a user, I'm a driver, I just want to go to my workplace as fast as possible. But if social optima is also considered, and should be on long term, because that's the main goal of sustainability in transportation. So if social optima is considered, we can achieve much more and balanced traffic. And this is a trade-off for the users, but benefit for the from social perspective. So what we did here is a multi-objective approach to balance these individual and social preferences in the traffic flow allocation problem. The methodology is again reinforcement learning based, and we used the Deep Deterministic Policy Gradient DDPG method. In this framework, the vehicles are agents utilizing this framework, and the network inputs are the states needed by the trajectory optimization algorithm, and the outputs are simply the actions to decide by the cars whether to keep or alter the current trajectory. So the state space in more details of the DTPG algorithm is as follows. First, the current driving trajectory of the agent vehicle must be calculated, the route, or must be known. Secondly, the value of the travel price function. We use a special utility function approach, so-called marginal cost for the current trajectory. Thirdly, the average waiting time in the entire network. So in general, what is the waiting time for cars, meaning the time when the car is not moving, so stopped at the traffic light and so on. And lastly, the average delay time. So delay is generally calculated in the traffic engineering world in a way that if we assume a free flow situation and we compare this free flow travel time with some other travel time with jam or not free flow, the difference will be the delay, of course. So compared to the either idealized situation, we can calculate the delay time. And so these are the four states in the state space which are considered in the algorithm. The action space works as follows. Once the agent receives the state, we apply again the SUMO, the microscopic traffic simulator, which calculates possible routing, so possible trajectories for the cars, for the agents. And for each car, the first three best ranked best trajectories are selected with the lowest cost functions. So in our case, the output of the action space are dictated in a way stay on its current trajectory, or switch to the first alternative trajectory, second or third alternative trajectory. So the outputs of the DTPGs tells the car, the agent, what to do as the next step on its route. The reward function, how the whole system is calculated, is defined in a multi-objective approach. So the agent attempts to reduce traffic congestions in general by maintaining or altering the current trajectories. And in this approach, we consider four aspects: safety, which means the following. safe following distance between consecutive cars. Secondly, the individual efficiency, which means the speed variation step by step. Thirdly, the social efficiency, which is sum of the waiting time and delay time in general. The comfort, which is the jerk, so the acceleration rate change, and fuel consumption as well, which was calculated based on the built-in model of the SUMO, which calculates the fuel consumption. So this reward function is recasted in a multi-objective way, where the total reward is a weighted sum of these aspects. And of course, the question is the weightings, but we made different experiments so we can compare how it works. So we did several experiments that I would like to emphasize two. One is called DDPG1, second is called DDPG2. So DDPG1 is the social routing approach, meaning that you can see the weights here. Actually, the weights for the social routing approach and individual routing approach are very similar. In this case, only the second and third terms are inversed. Second term and third term, recall again. Second is the individual efficiency, third is the social efficiency. So these two reward parameters are weighted in a different way in the social aspect and in the individual routing aspect. And this is compared via SUMO traffic simulation. We did experiments on a well-tuned network, which is available freely. Fortunately, this is a Luxembourg traffic network, which was validated based on several thousands of floating car data. And this is a typical European road topology with traffic lights, with lot of with freeways, with secondary, with highways, with secondary roads, with residential zones, with traffic lights. So it encompasses a big variety of road topology, and real-world mobility patterns are used in this. We use this scenario to simulate our algorithms, and we run with different traffic demands. And the overall performance of the DDPG algorithm and other routing algorithms can be seen here. So on the left figure, you can see the average speed variation along the traffic flow. You can see 4 algorithms comparison. One is the shortest path routing, second the Dijkstra algorithm for routing, and the DDPG2, which is the individual RL-based routing, and the DDPG1, which is a social routing with reinforcement learning. And this is the best in terms of average speed, you can see, and also in terms of average waiting time, the less waiting time can be achieved with the social-based routing. So, but even with the individual routing, with the it's also red, but not so light red color curve. So you can see the individual routing DDPG2 has also considerable improvements over the conventional routing methods. And another interesting result, because these two simulations were run assuming 100% automated vehicles, so all vehicles follow the rules what we dictated. But here you can see some analysis concerning the AV penetration rate. So the ratio of autonomous vehicles compared to the human driver vehicles. And from left to the right, you can see the ratio by quarters. And as expected, fortunately, DDPG 1 and 2 has more and more better results and benefits if the ratio of automotive vehicles increases as well. So that was the network level solution for traffic management. And what we can conclude that RL-based methods can be efficiently applied with the capability of online learning, which is very important, and model-free solution. We demonstrated both solution with high fidelity traffic simulation with the SUMO, which also justify that this is these are viable solution in future intelligent traffic management. And our future work consists of integrating the two, so the intersection and network level approaches. That was my presentation. Thank you. And if you have any question, please free to ask.